We are about to begin the study of fluids and how fluids can be used to do work, how we can apply the physics of fluids to do all sorts of useful things. So first of all, let's begin with what is a fluid, nice and simple. Well, a fluid is something that can flow, something that can easily flow. So generally speaking, solid objects do not flow. They are rigidly held together by their intramolecular bonds. So things that flow are restricted to liquids, which of course makes sense. We often think of liquids as fluids. Doctors say, make sure you drink enough fluid, right? But also gases. We sometimes forget that a gas is also part of the category of fluids. We don't think of gases as fluid because we think just liquids, but don't forget, fluids and gases. Fluids are liquids and gases, I mean to say. So now let's look at liquids and gases and a little bit of their properties. First of all, if we look at gases, there's an interesting thing about gases, and that is that if you put pressure on a gas, what can happen is the molecules between a gas are very spread out. The gas molecules have so much energy that they can sort of overcome any of the intermolecular attractive forces holding them together. So gas molecules are free and easy. They can go just about anywhere they want, which means there's a lot of space in between the molecules. And so that means that if you put pressure on the gas, okay, pressure on the gas, let's put, we'll confine this to a, and we'll pretend that these walls are closing in. So the gas is feeling pressure from all sides. What happens is the molecules of the gas can be pushed closer together. So there is less space between them. So the space in between, right? Now, the closer you push them, the more the forces in between begin to resist. So you can only push so far. You can't keep pushing indefinitely. But gases sort of have this sponginess about them that when you push them, what can happen is the molecules will sort of squeeze together, and we say that the gas can be compressed. So I'm going to use that word here, compressed. Gases can be compressed. Whoops, let's spell it right. Gases, sorry, can be compressed. Compressed. They can be squished a little bit, actually a fair bit. And that's important because if we look at a liquid, it's a little bit different. In a liquid, the molecules are already pretty close together. See, the difference between a liquid and a gas is the energy. Remember, we talked about heat being energy. And when you heat things, you change them from liquid to gas. So the heat supplies energy, which causes the molecules in the gas to be far apart. But in the liquid, there's less energy, and the intermolecular forces are holding on more tightly. So in this case, there is not much space between the molecules at all. There's some, but these molecules, if you try to squeeze them, these forces are, I'm drawing these little blue lines to represent the forces in between the molecules. If you try to squish this gas, or sorry, this liquid, maybe we should write the word liquid here so we remember that we're now talking about liquid. What happens is not much. It's very hard to squeeze. Those spaces, those forces are going to resist your squeezing. So the liquid doesn't squeeze very much. It might squeeze a tiny bit. There's always some, right? But we're talking about not enough to really matter for most normal applications. You can't really compress a liquid. So let's write that liquids are not, whoops, look at my writing today, are not very compressible. It's very hard to compress. That's an ibble. Not very hard, or it's very hard to make a liquid compress. Now, that doesn't mean you can't put it under pressure. You can still put a liquid under pressure. But if we think about what happens, if you take a gas and you put this simple piston, right? So a piston is basically a movable, sort of like in a syringe. If you think about a syringe for when you get a needle from the doctor, the little black thing inside, right? It seals, it rubs up against the container very tightly, but it's movable. You can push it up and down, but it doesn't let any of the gas or the liquid escape. So if you have a gas in here, right, and you try to push down on it, well, the piston will actually be able to move a fair amount. Because what will happen is, whoops, let's make that piston go all the way. Let's seal it off. There we go. So there's my piston. What will happen is the gas molecules will just compress and get closer together. So you can push the piston down a fair bit with a gas, right? But with a liquid, if you try to do this with a liquid, put the piston here at the top, I'll color it all in. So with a liquid, what happens is the molecules are already pretty close together. So when you try to push down, you apply pressure and the liquid becomes pressurized, but the piston doesn't move much. The piston, it will be very hard, almost impossible, to push this piston down through the liquid. You can't get any kind of compression on the liquid or cause it to reduce in volume. Maybe that's a good way to put it. We can make a gas reduce its volume and become higher in pressure, whereas a liquid tends not to. And that's an important thing. So if you push on this, the only way that something can happen is if you have an outlet where the liquid can go. And what we're going to see is by giving the liquid an outlet and making it go to somewhere else, we can actually use the fact that it won't compress to make something else happen. And we'll get to that in a minute. So that's an important thing to remember, that liquids are not very compressible, but gases are compressible. We talk about fluids. All right. The second thing is some new words. Typically, when we talk about liquids, right, we use and liquids being specifically applied to doing work for us, we call that hydraulics. So a hydraulic system is something that's using liquid under pressure, not compressible, but under pressure, to do work for us. And you can see the word hydro in there, hydra, which makes you think about water, which is a liquid. If we talk about gases under pressure, pressurized gases, that's called pneumatics. You can think of this like pneumonia, when your lungs get sick, get filled up with stuff, but your lungs are all about breathing gases. So the word pneumo means gas. So we have hydraulics or hydraulic systems, and we have pneumatic or pneumatic systems. Both of these are fluid systems, right? Both are fluid systems, but they're a little bit different because of the fact that gases can be compressed and liquids cannot. Okay, so now let's talk about the concept of pressure. Pressure has to do with force, but it's very particular. It's when you take a force and you push on something, the pressure you make depends on how much area the force is spread out over. So I'll give you an example. If you cut your steak with a knife, a sharp knife, let's look at a knife. Here's a knife sort of in cross section. So here's a knife, and here's your steak. Well, if you think about applying a force, let's say you push on this knife, all of that force is concentrated at a very small point. If we think about the knife blade, all along the knife blade, it's just an edge. So what's the area of that edge? Well, it's not very much, which means that all of the force is concentrated on a small area, which means that the steak will cut. The knife will push through. But if you take the side of a fork, it's kind of flat on the edge. There's the side of a fork. It's flat. Here's your steak. Well, now you're pushing, but it's spread out over a larger area. So it might be the same amount of pushing, the same force that you're pushing down on the fork with, but it doesn't cut as easily because the pressure is not the same. The pressure is the force spread out over this entire area. And that has a different effect. Another good example is if you think about when you walk, here's your the footprint of your boot, sort of like this, and then maybe you have a heel on your boot, or maybe your boot is just all one thing without much of a heel and the sole is all together. Okay, so that's when you step on the ice. All of your body weight is pushing downwards into the board, but it's spread out over the area of your feet, of your boot. But when you get on a pair of skates, skates have a thin blade so that only this thin blade is touching the ice. That's a lot less area. Now you weigh the same, so the force pushing against the ice is the same, but now that force is concentrated over a smaller area on your skate, which means that the pressure on the ice is much, much bigger. In fact, it's so big that it actually causes the ice to melt a little bit. And when you skate, there's a thin, thin layer of water under your skates, which is why they're so slippery and they glide for so long. But it's such a thin layer that as soon as you glide by and the pressure is released, it refreezes very quickly. So it's not like skating melts all the ice. It melts it temporarily under your skates, but only when there's a heavy pressure. Then it refreezes. So the skate means that, again, the smaller amount of the area, the greater the pressure. So what that means is pressure goes up as force goes up. And the way we write that mathematically is with what we call a proportion statement, right? So we say pressure is proportional to force. So what that means is if you increase the force, then the pressure will also increase. They go together. But with area, we say that the pressure, so I keep writing equals, the pressure is proportional, we say, proportional to the inverse of area. This is how we write. So what this means is that if the area goes up, the pressure goes down. It's a reverse kind of relationship, see? In this relationship, they both work together. Pressure, force up, force down, pressure down. Here, area up, pressure down, pressure up. So you see how the area went down when we used the skates. So the pressure went up. And the way we write the two together is in a mathematical formula where we write that the pressure equals force per unit area. Force per unit area. So it's force spread out over an area. And then if you just think about the units, well, you have newtons is the unit for force on the top, and you have meters squared or square meters on the bottom for area. So the newton per square meter is the actual unit for pressure. But we call it something else, just like we do with lots of other. The newton itself is a kilogram meter per second squared, right? And so we call this unit a Pascal. So a Pascal is a unit of pressure. It's 1 Newton spread out over 1 meter squared. That's called a Pascal, 1 Pascal. And it's not very much, not very much at all. The symbol for a Pascal is a PA, like that. So that's the unit that you'll see measuring pressure. And we'll get more into the mathematics of that later. So we could do a simple pressure calculation. We could do, how much pressure is being exerted by an object. Let's talk about you. Let's see. Well, we could say the bottom of your boot, and to make it simple, we'll make a rectangular boot, and we'll calculate the area. So if you think about a typical shoe or boot, it's maybe about 8 centimeters across and not quite a full foot the other way. Maybe I'm going to say 30 centimeters. No, that'd be too much. Let's go 20 centimeters, 25. 25 sounds good. 25 centimeters down this way. Maybe it's a small kid's foot or something. So 25 centimeters this way. So the area, well, we want meters because everything has to be in our standard unit. So the first thing we do when you're dealing with this is make sure you have units in meters. So 8 centimeters is 0.08. And then we're going to multiply that length times width for area, right? So 0.25. We have to do the multiplication. So make sure you do your conversions. I think that's going to come out to about 0.02 square meters. Okay, so that's the area that your weight is spread out over. So now we can think about you standing up. Here you are. Okay, well, your weight is the force down, which is the force of gravity. So the force of gravity is the weight, and we know how to calculate that. It's mg. So let's say that you have a mass of about 30 kilograms, 35, 40, whatever you might be. So we put 30 kilograms, and we put, of course, g is 9.8, and then you can multiply that out, and that's pretty easy. That comes out to 294 newtons. And so now you can figure out how much pressure you are exerting on the floor by saying force over area, and that would be 294 divided by 0.02. And it's actually a pretty big number. It's going to come out to 14700 pascals. Now, since pascals are a very small unit, we often get big numbers. And so sometimes we will just use the metric system and use the prefixes. Like you can have a kilopascal, like a kilometer, right? And so if it's the same thing, this would be 14.7 kilopascals. So that's often how we report pressures, as kilopascals, just to keep the numbers from getting too big. So you'll see that a lot. Now, it doesn't have to be your weight. This force happens to be weight when you're standing on something, but that could be anything. You could use any kind of force. You could push on something. I can push against the wall and create a pressure. And as long as you knew how much force you were pushing with and the area over which you were spreading it, right, then you could actually figure that out, no problem. And in fact, if you think about standing on the ice on top of a lake, all right, when you stand, let's say this is how much pressure you exert on the bottom of your feet. Well, what happens if the ice starts to crack? Because that's too much pressure. And you get scared that you're going to fall in the water. Well, one thing you can do to maybe help yourself out is to lie down on the water or on the ice. Because when you lie down now, think about it. There's going to be a bit of your head that's sort of touching the ice. Maybe parts of your shoulders are going to touch the ice. Not your whole body, but parts of your back, right? So in other words, and then maybe some bits of your leg. Not every part of you is going to touch the ice, but a lot of it. Okay, now let's add up all this area. Well, that's a heck of a lot more area than the bottom of just your feet, isn't it? So let's think about that. If we do really rough calculations, maybe this is, about 10 centimeters by 10 centimeters for your head. Maybe the bunch of your back is touching, maybe that's 20 centimeters by 30 centimeters. And again, I'm just guessing, right? And these are not squares, but if you sort of imagine them as the sums of squares, just to get an idea. And down here, your legs are touching. Well, maybe that's about 0.3 centimeter, 30 centimeters by, maybe 30 centimeters. So this is 0.01, right? And then you multiply the other, that's 0.06, right? 0.2, so put that as 6. And then 0.3 times 0.3, 0.09. So when you add all that up, 9 and 6 is 15, and 1 is 16, carry the 1, there is the new area. Look at the difference. You've increased the area from 0.02 to 0.16. Now, it's still the same weight, 294. But if we calculate the pressure now, it's 294 over 0.16, which is going to give us a much different number. I'll just quickly do that. So that's only 1,800 and rounded off to 38 pascals, or 1.8 kilopascals of pressure. That's a lot less, isn't it? 14, it's only 1.8 now. It's much, much less. Look at the two numbers. So if this much pressure is cracking the ice, maybe you might have a chance to reduce the pressure this much by lying down, and maybe the ice won't crack, and then you can sort of wiggle along to thicker ice. That's why they say that if you're on the ice and you hear a crack or something, you can... now, it's a gamble. Maybe this is still too much to crack the ice. We're not sure, but at least it's better than what it was before. So you can see how the area makes a difference. The larger the area, the more the area gets to be, I mean to say, that means that the force is spread out, so there's less force on each little bit of area. And that's what we call the pressure. So the pressure actually drops if you make the area bigger. Now, of course, if you make the force bigger, the pressure gets bigger. Just like we said, that's the relationship I was talking about right up here, right? Force bigger, pressure bigger, but area bigger, pressure smaller. So that's a very important thing for you to understand. And that's sort of the basics of the introduction to fluids. In the next video, we're going to learn about how we can use this idea of pressure to do work for us. And we'll get into all those details later. We'll just call this the introduction video, and we'll stop it there.